Good morning, good afternoon, good evening, wherever you are. Welcome to this week's edition of HoloTube. We're very happy that Sebastian Grieninger is with us live from Stony Brook University, and he's going to tell us about critical and near-critical relaxation of holographic superfluids. Here you go, Sebastian, the floor is yours.
Yeah, thank you very much for the invitation, even though it was a little short notice, and for giving me the opportunity to give a HoloTube talk here. And I want to talk about some of my recent work on relaxation of holographic superfluids. And this work was done in collaboration with Mario and Sergio. And during most of the work, we were all still at IFT in Madrid. Okay. So in 2003, Ginsburg and Abrikosov got the Physics Nobel Prize together with Leggett for their pioneering work on superconductivity and superfluidity. And in particular, Ginsburg wrote together with Landau a phenomenological model down that was able to explain the macroscopic properties of superconductors. And later on, it was shown by Gorkov that this macroscopic model follows from the microscopic BCS theory in a certain limit. And Abrikosov, this is this gentleman here, used this phenomenological model to find vortex solutions, and he showed how magnetic flux can penetrate a certain class of superconductors. And time-dependent Ginsburg-Landau theory is one of the most studied and applied nonlinear phenomenological equations in physics, in the physics community. And the applicability ranges from nonlinear waves to second-order phase transitions, superconductivity, superfluidity, and Bose-Einstein condensation. And there's a second equation I want to talk about today. That's the Gross-Pitaevskii equation, and it's kind of the superfluid counterpart. And both are simple phenomenological models that are widely used and in some sense universal. And the microscopic image you can see here are vortices in some thin film material. Okay, let me tell you what motivated us to begin this project. So if you think about the time dependence of homogeneous superfluids near the phase transition, then the time derivative of the order parameter phi is given by the derivative of the free energy. So what happens if the derivative of the free energy vanishes, like it does, for example, at the critical point, because then the right-hand side of that equation is kind of zero. So, and since this is HoloTube, I think it's fair to immediately talk about holography, and let me tell you about the holographic analog. So if we think about the quasi-normal modes, which are solutions to the linearized equations of motion for fluctuations at zero sources, if we think about them at zero wave vector, then the quasi-normal mode that describes condensate and amplitude fluctuations goes into the origin of the complex plane once we reach the critical point. So it becomes massless and there's no exponential decay. So how does the system approach the equilibrium? Like what governs the relaxation? And as you can see from this equation, if the derivative gets smaller and smaller the closer we get to the critical point, so the right-hand side becomes smaller and smaller, and even if there's an exponential fall-off, the half-life time diverges and it takes longer and longer to get to equilibrium, and this is known as the critical slowing down. If we were to think about experiments, then it would be, of course, extremely difficult to engineer a system that relaxes exactly to the critical point. And for this reason, we are also thinking about something called near critical quenches, which means quenches that end near the critical point, either in the superfluid phase or slightly in the normal phase. And here you can see two types of relaxation. The red curve shows a purely exponential decay, while the blue curve is a power law that's going over into an exponential decay. And you can see the blue curve is much slower. And once the argument of the exponential gets smaller, it's going to take longer and longer to reach equilibrium. And yeah, it's very timely to think about these things. First of all, the order parameter fluctuations, which drive the relaxation back to equilibrium, are usually neglected in usual hydrodynamics since they are described by massive modes. But close to the critical points, those modes become very light and have to be taken into account. And for example, there are recent experimental results in the context of strange metals where those order parameter fluctuations play a role. And on the other hand, there's also a push to use holographic models to help the phenomenological model building. And two groups tried to classify dissipation in holographic superfluids, and they tried to fit the Pitaevskii equation in order to pick and build a good phenomenological model that's relevant for vortex experiments to describe vortex dynamics. Okay, let me get to the plan of today. So first I'll review some basics and talk about the state of the art. Then we'll proceed and we study the phenomenology of critical quenches numerically in a holographic model. Then we'll use this intuition to build our phenomenological model in the boundary theory, which describes the homogeneous dynamics. So we won't talk about any spatial dependence. We determine the input parameters of our phenomenological model in our holographic model, and then we'll use this phenomenological model in order to predict the nonlinear time evolution and double check with the time evolution we can do in holography. Okay, and yeah, let me maybe emphasize this. We don't just fit an equation, we actually determine the parameters from the static response and linear response theory. And then we use this to predict the nonlinear time evolution. So it's not just a fit to the time evolution. It's kind of independent in that sense. And there's of course a shortcoming of our study. If we are in the large N limit, which means the fluctuation near the critical point are suppressed by the large N limit, and we only see mean field physics. But in the end, holography provides us with a first principles description of non-equilibrium dissipative dynamics at finite temperature. And I think that's something very powerful. Okay, so how does the time-dependent Ginzburg-Landau equation look like? The time derivative of some complex function psi is related to the Laplacian. Then we have the function itself, and we have a cubic term in psi, which describes nonlinear dispersion. And in the presence of external vector potentials, we of course have to replace the normal derivatives by gauge covariant derivatives. So we pick up this effective potential here in the time derivative and the spatial components of the gauge field and the spatial derivative. The Pitaevskii equation looks pretty simple, and I took those two equations here from this recent holographic paper, and they include the dissipation into the equation in a different way. So in the first equation, you can see dissipation is included by this parameter gamma on the right-hand side. And this supposedly incorporates the Keldysh self-energy through the fluctuation dissipation theorem. And a second way to do this is to include this parameter eta with the time derivative on psi squared on the left-hand side. And this parameter comes from imposing the second law of thermodynamics. But I don't want to talk too much about this. So before we talk about the state of the art, maybe let me talk about the methodology. So there are of course different approaches to strongly coupled field theories, and they all have advantages, shortcomings. But since we want to investigate non-equilibrium dynamics at finite temperature, I think the appropriate toolkit is holography. So holography states that certain quantum field theories in d spacetime dimensions are dual to quantum gravity and ADS-D+1. And if you kind of sketch this out, then you have your field theory here, which is living on the boundary of that higher dimensional space with the gravity theory. If we work at finite temperature, we include a black hole horizon on the other side. And the statement of the duality happens on the boundary where the field theory lives, because there we equate the two generating functionals. There's kind of a problem because we don't have the field theory under control. We don't really know what quantum gravity is. So it's probably good to take a certain limit. That's the large N limit in the field theory. And that translates into taking the limit of classical gravity on the other side. If we want to compute the phase diagram at finite temperature and finite density, then in holography, we have to consider charged black holes with Hawking temperature T. We can probe linear response. For example, the poles of the retarded Green's function correspond to so-called quasi-normal modes of the black hole. Those are perturbation, and you measure how the black hole rings down back to equilibrium. And we can also study the whole non-equilibrium dynamics by evolving the whole geometry in time. So in the invitation, I was asked to speak a little about the state of the art. So there are two groups who recently investigated vortex dynamics in terms of the Gross-Pitaevskii equation. And here you can see a picture of the initial configuration. You see those two vortices in the boundary, and it's taken from this first paper here. And the vortices, it's pretty cool. They stretch all the way down to the horizon, and you can see their bulk dynamics. And those two groups studied how those vortices evolve in time. And yeah, they fitted the parameters of the dissipative Gross-Pitaevskii equation from the holographic data. And I think it was done with the motivation to select a phenomenological model. And one thing I find a bit curious about is that they work at fixed chemical potential, because for me, that's an equilibrium concept. In the context of holography and quenches and Kippel-Zurich mechanism, there are a lot of very well-known papers. And all of these papers study quenches from the normal phase into the superfluid phase across the phase transition, most of them with spatial dependence. And they monitor the defect formation. Like you can see in this picture panel here, you quench from a normal fluid into the superfluid phase across the phase transition, and you see those topological defects building out. And there's a prediction from Kippel and Zurich, and the idea here is to use holography in order to test this phenomenological prediction. Okay, let me talk about the holographic model that we are going to use today. So the so-called holographic superconductors are probably the most studied and well-known model in applied ADS-CFT. And even though people first called them holographic superconductors, we should probably refer to them as superfluids, because the gauge symmetry in the bulk translates to a global symmetry at the boundary, but we could view them as weakly gauged superconductors. Okay, so I will explain everything to you in the so-called probe limit, which is the large charge expansion, which makes things easier, and we only consider the probe limit anyway, so let's not make it more complicated than we have to. So we keep our background geometry fixed, and all the matter content is not going to backreact on the background geometry. We want to include a radial electric field on top of a fixed ADS Schwarzschild background. And this radial electric field induces a chemical potential and a finite charge density in the dual field theory. And the black hole means we work at finite temperature. We also include a massive scalar field, psi, that is charged under the gauge field, under the U1 gauge field A. And the action looks as follows. So we have the gravity part that we keep fixed. That's just the Einstein-Hilbert action that gives us ADS. Then we include the U1 gauge field, which has the Maxwell action here. and we couple the massive scalar field to it, and the scalar is charged under the gauge field with the gauge covariant derivative. As an ansatz, we switch on the temporal component of the gauge field, which gives us the chemical potential and the charge density. Then we have the complex scalar field here, and our background metric is the fixed ADS4 Schwarzschild black hole in infalling Eintake-Finkelstein coordinates. And from this metric, you can read off the temperature. If you look at the blackening factor, that's the function multiplying dt squared. You just look at the derivative at the horizon, which is at u equals 1, and you find the temperature. So our radial coordinate, which is the extra dimension of ADS, is chosen in a way that it goes from 0 to 1. And the boundary is located at u equals 0, and the horizon is located at u equals 1. And our field theory coordinates are t for time, x, and y for the two spatial directions. The equations of motion associated with this are, of course, the Maxwell equations and the equation for a massive scalar. And if you look at the static case, they have a very simple solution. You find, because if you set psi to 0, then the scalar equation is solved. And then you find the trivial solution for the temporal component of the gauge field, which is just proportional to 1 minus u. And this proportionality constant here is the chemical potential. And we refer to this simple solution as normal fluid. And from this mu, you get this radial electric field that stretches through the bulk. If we consider time-dependent fluctuations of the scalar field about this background at 0 wave vector, then you'll notice something interesting. Once you turn up the strength of that radial electric field, which means increasing the chemical potential, the quasi-normal modes cross into the upper half plane. That indicates some instability. So what's happening here in the bulk? And pretty early on, Gapsa noticed that if you have an electrically charged black hole, then the effective mass of the scalar depends on the radial direction. So once the radial electric field, which enters here and it enters negative, becomes large enough, the effective mass becomes negative enough near the horizon, and the scalar is able to destabilize, and the black hole becomes unstable towards forming scalar here, and the scalar actually condenses. And there's this beautiful geometric picture, which is taken from a paper of Gapsa and Pufu about P-wave superconductors. And so the scalar is unstable near the horizon, so it forms out a radial profile and is no longer 0. So it condenses near the horizon, which means we have a superconducting condensate that floats just above the horizon. And this superconducting condensate is balanced, one by the gravitational force and by the electrostatic force acting on it. And since the condensate only carries a finite fraction of the whole charge density, there's a lot more above the condensate than near the horizon. So if we consider some charged particle psi plus, then this particle is driven upwards by the electrostatic potential, which is this E field here. But it can, because of the warp geometry of ADS, it cannot escape to the boundary. So it either stays and has to participate in the superconducting condensate near the horizon, or it falls into the black hole. And yeah, that's how the holographic superconductor is realized in a bulk picture. Okay, as usually in ADS CFT, all quantities are extracted at the boundary. So if we choose a mass for the scalar, then the asymptotic expansion of this supergravity field near the boundary look as follows. So the leading part of the scalar goes linear in the radial coordinate, and the subleading mode goes like u squared. And it's similar for the gauge field. It goes as constant plus linear in u. And the constant here is identified with the chemical potential, and rho is interpreted as the charge density. Since we want to have spontaneous symmetry breaking, we have to set the source of the scalar to 0. The scalar source would break the U1 explicitly. And once this subleading part here becomes non-zero, and we don't switch on the source, we have spontaneous symmetry breaking because the subleading mode here breaks the U1 spontaneously, and the condensate is encoded in the subleading mode. It's pretty straightforward to compute the phase diagram for this, and I think you've all seen it. So close to the phase transition, the condensate falls off like in a mean field ray, and I show you here the condensate as a function of rho near the phase transition. And the mean field exponent is just 1/2, as we would expect, I guess. Okay, so what we are interested in our work are quenches in the charge density, and we want to start at some point in the superfluid phase, as indicated in red here, and we want to quench the charge density in a way that our final state will be exactly at the critical point or near it. So this green dot is our final state, which would be exactly on the phase transition. Yeah, and from now on, we'll consider only strictly homogeneous setups. So there's a problem if you look at the radial Maxwell equation, because of course, if you evaluate the radial Maxwell equation at the boundary, then you'll find charge conservation because we have only a spontaneously broken U1. So if we want to move throughout the phase transition, we have to kind of do something to that equation because it tells us we can change the charge density, which wouldn't allow us to move through the phase diagram. And one way to have the time derivative of rho not equal to 0 is by switching on a scalar source and doing a quench in that scalar source. And that was done in this paper here. But this scalar source explicitly breaks the U1, at least for the time being where you perform the quench. There's another way to engineer this. And what you can do is you add an external source to your system. So what we add to our action is the so-called null fluid action. It adds an AMU and an external current to it. And with that external current, we can change our charge density at will. And we add this null fluid action by hand, and we obtain something like radial-like solutions. Okay, so after adding this null fluid action here, then you can see the radial Maxwell equation, which is the constraint equation, is modified. We have this external source on the right hand, and we can drive our system. So let me quickly tell you how our quench profile looks like. We perform quenches in the charge density, and they look like step functions. And this is given by this expression here. So the rapidity of our quench is governed by this capital omega, and the center of the quench is determined by this time Ts here. And shortly after the quench, the external source will be switched off, and the charge density will be constant. So we'll have our charge conservation again. And it's important to notice that at the intermediate and the late time behavior are all independent of the quench protocol, as I'll show you later. So it doesn't really matter how we quench it. Of course, we have a system of PDEs that has to be solved numerically. And I think it goes without saying that if you solve something numerically, all equations and constraint equations should be satisfied at all times and all points in space. Okay, let me show you how this charge density looks like. So here I show you a typical quench. I show you rho as a function of time. And this NZ here is a zoom in on the early times where you can see the step function. And the reason why this isn't centered around 0, it's for numerical reasons. So we have to let some time pass before we can do the quench. And as you see, like for times bigger than 1.6 or 1.7, the charge density is just constant. Okay, so we have a system of partial differential equations that has to be solved numerically. And usually if you look at time-dependent problems, then you combine pseudospectral methods in spatial directions with a fourth order Runge-Kutta or Adams-Bash fourth in time direction, and they are both explicit time matching algorithms. Our problem requires a stable simulation over large time intervals. So, and ideally, since the dynamics get slower and slower, we are able to make our time step bigger and bigger at late times. So we need an implicit algorithm. And the reason why I'm showing you this slide is because we use pseudospectral methods in space and time, which is something that's usually not done. And that's a highly implicit code. It's highly accurate, and depending on how many grid points you choose in time direction, your order of the your order increases in time direction. This whole thing is in the multi-domain spirit. So you take your time interval, you split it in multiple domains, and you can adjust the size of those domains, which is basically your step size, dynamically, depending on how much is happening during the previous time step. And we use the Chebyshev-Lobato grid in radial direction, and in the time direction, we use something called right-sided Radau grid, because it doesn't include the initial time slice. And if you're curious about this, this was pioneered in this paper by Hennig and Ansorg, who was a professor in Jena, and I learned about it during my master thesis. So we applied this in holography for the first time in those two papers, and we use it today. But that's just a side comment. Do we have any questions so far? Okay, I talked a lot, so let's finally get to some results. So we look at exactly critical quenches. So we start in the superfluid phase, we quench to the critical point. Okay. And yeah, in holography, the quasi-normal mode that drives our relaxation becomes massless. So there's no exponential decay if we approach the critical point. So what is happening here? And since linear response seemingly breaks down, this relaxation is purely encoded in the nonlinearity of the equations. Okay, what you can see here is the order parameter as a function of time for quenches starting at different points in the superfluid phase. So we have one quench starting at a condensate of 1/2, and we can go deeper in the superfluid phase by increasing our initial condensate up to 12. And what you can see here is they all go to the same straight line, independent of where we started or what kind or how fast the quench was. They all fall off the same at intermediate or late times. And this is a double logarithmic plot. So this straight line means that we see a power law decay. And if you fit this, then you find 4.07 for the amplitude and and the exponent of the decay is -1/2. You can take the same data, and instead of the absolute value, as I showed you here, we can plot the real and the imaginary part. And you can see those usual oscillations in the decay, but unlike usually, they are not on a linear scale in time, but they're on a logarithmic scale in time. And from this data, you can extract the phase. And if you look at the time dependence of the phase, then you find that it goes logarithmic. So you have log periodic oscillations. And those are usually an indication of discrete scalar invariance. And I should probably mention this same power law behavior and log periodic oscillations were also noticed in a somewhat related paper about the Kondo model, where those authors looked at critical quenches. So it becomes even more clear if you plot the real part versus the imaginary part. You see this fractal structure, how it like spirals in. And one characteristic thing for discrete scalar invariants are complex critical exponents, like we see here with the log periodic oscillations. And those are self-similar systems with a fractal structure. Okay, we should also do the same for the gauge field, and you can see exactly the same as for the absolute value of the order parameter. We can either look at AT directly or at the gauge invariant combination of time derivative of the phase and AT. And all curves tend to the same line. This time they decay with exponent -1. And you find for the amplitude 0.93. So we found scaling solutions to those equations with exactly those scaling exponents. And one thing I was wondering about is if it's actually possible to find analytical solutions in the bulk. But enough of holography for now. Let's try to build our phenomenological equation in the boundary. So this is for the homogeneous case. So we don't look at any spatial derivatives. So in that sense, it's only a first step because of course it would be nice to have the full spatial dynamics in there too. But since those equations are very universal, I think this could have some implications or important implications beyond holography because it's a very universal equation. So how does this equation look like? If you look at it closely, then you see it looks very similar to the dissipative gross Pitaevskii equation or some corrected Ginzburg-Landau model. We have the time derivative acting on our complex function psi, and this here is the gauge covariant derivative. Then again, we have a function cubic in psi, and we splitted it up to two sides. So one part is on the left side, the other part is on the right side. And we also have that term linear in psi that we had before. And you should keep in mind the psi is complex. So that's actually two equations because we get one equation for the real part and one equation for the imaginary part. And after you split psi in its modulus and phase, then all appearing parameters or quantities in that equation are considered to be real. So this complex prefactor here, it includes dissipation and it models the phase rotation. We neglect all higher orders of psi, and this is kind of an expansion close to the critical point. We expand in rho instead of mu. So if you think back about the Gross-Pitaevskii equation, we had a mu here. We use rho instead because we work in an ensemble at fixed rho. We neglect all spatial derivatives. Then if you do the split, then the equation for the modulus decouples, and you can solve it analytically, which I'll show you at some point later. An assumption for this equation is that the charge density is constant in time. So that's only satisfied in the holographic model after the quench. And of course, C1 is trivially 1 because that's just the parameter of our gauge covariant derivatives. Yeah, the claim is that we can describe this is a nonlinear equation. The claim is that we can describe the nonlinear dynamics. And this equation should be valid close to the critical point. So where the modulus is small and where deviations from rho with respect to the critical charge density are small. Otherwise, we'd need higher order corrections. Okay, we can fix all parameters of that equation within linear response theory. and from the properties of the equilibrium state. And this is a big advantage because, of course, it's much easier to construct static solutions and just look at linear response than doing the full real-time evolution, which is computationally a lot more expensive and hard to do. And our goal for the rest of the talk is we determine the parameters, and then we make a prediction for quenches and cross-check with the real-time evolution for sub, super, and critical quenches. Okay, do we have any questions now? Okay, so let's determine the parameters. I'm gonna jump back a lot back and forth between holographic model and phenomenological equation. So if it's too fast or if it's not clear what is what, please just stop me and ask. It's easy to see if you did all the fits, but it's probably very hard to follow if you see it for the first time. Okay, let's look at static solutions to this equation. And of course, as I told you, it's a complex equation. It's actually two equations. So both real and imaginary part have to vanish. We replace the psi by modulus and e to the I phi. Phi is the phase. They're both phi. The phi in the exponential is the phase, and this is the absolute value of the condensate. So to have a static solution, we find that the modulus goes like the square root with this parameter C4 times rho minus rho C. So the parameter C4 kind of models how the condensate depending on where we are in how big the condensate is, depending on how far we're from the critical point in terms of rho. Then after solving the real part, we can look at the imaginary part of the equation. And here we have AT equals rho minus C5 phi squared. So the C5 kind of models how the chemical potential mu, which is labeled AT here, deviates from rho in terms of the condensate in the superfluid phase. I hope that's clear. Okay, then we go to holography, and of course it's very easy to determine those parameters there because they just follow from thermodynamic quantities. We construct the phase diagram near the critical point, and then we can just fit the expectation value, which is the condensate, to this expression. And we also know what the chemical potential is and rho, and we get two numerical values for C4 and for C5. And as you might have noticed, the dimensions go a bit back and forth here. So rho is dimension 2, mu is dimension 1, O is dimension 2, and it's squared. So all those dimensions don't really match. But we assume that all physical quantities here are normalized to appropriate powers of T bar, which is conveniently 1. So it's pretty straightforward to get the dimensions back at the end. So all those constants here aren't dimensionless, but they actually have a dimension. Okay, let's determine the parameter C2. And to determine this, we actually have to look at linear response theory. We can solve the phenomenological equations analytically for solutions in the superfluid phase or in the normal phase. And if we have that analytical solution, which I don't show you here because it's messy and not very illuminating, then you can do a late time expansions. And for quenches ending in the superfluid phase, you find at late times that the phi minus this combination here decays exponentially with this expression. This is the exponent. And similarly, in the normal phase, you just find the pure exponential decay. Because of course, here in the superfluid phase, your phi will have some finite value at the end, while in the normal phase, the phi should just go to 0. we have two exponential decays. And of course, we know how to determine them in holography. It's just looking at quasi-normal modes and looking at the frequency. So in the superfluid phase, we look at the quasi-normal modes at 0 wave vector, which are the linearized fluctuations. And in the superfluid phase, this is the amplitude or Higgs mode, which is a gapped mode. And if you fit this as function of rho minus rho c, then you find this red expression here for this amplitude mode. And you see as rho approaches rho c, this goes to 0. And this number in red here is related to the exponent that I showed you up here, because this omega is in the e to the minus I omega t, which should be set equal to this exponent here. Similarly, in the normal phase, we look at the decay, at the exponential decay of the order parameter. So we should look at the imaginary part. In the normal phase, the quasi-normal modes are fluctuations of the complex scalar, which are also massive modes that also go to 0 if you go into the critical point. And this red number here should be compared to the exponent up here. And luckily, they both yield the same numerical value for the constant. So that's already a non-trivial check, because we can determine the constant either in the superfluid phase or in the normal fluid phase from the exponential decay of the analytical solution to the phenomenological equation. Okay, then there's one parameter left. And it's very easy to see how to determine this parameter for the normal phase, because for the late time behavior for final states ending in the normal phase, you see that the phase, the time derivative of the phase decays like this. And you should keep in mind the phase is in the exponential, so we can actually also compare this to the quasi-normal mode. And this time we don't look at the imaginary part, but we look at the real part. And this is exactly the same quasi-normal mode as I showed you on the slide before. So the numerical value for this constant is just a 0, follows from this by comparing to this expression here. It's a bit more complicated for final states in the superfluid phase. So here I actually wrote down the late time expansions of the analytical solution. And if you look for, we want to determine C3, then you see it appears in the prefactor of the exponential decays. So what we can do is we can build the ratios of the prefactors of the exponential decays, and then we find an expression for the C3. And those require us to determine the amplitude of the exponential decays. And you might wonder how to do this in holography, because it's not the quasi-normal mode, but like the amplitude multiplying the exponential decay. And it's actually possible to compute this within holography. And if you don't know this, then you should read our paper from the last year where we laid out this framework. So quasi-normal modes, when we compute them numerically, they are the eigenvalues of a generalized eigenvalue problem. The generalized eigenvalue problem can be written in this form, where A omega minus B times X is equal 0. So A and B are your differential operators of the problem. Omega is the eigenvalue that you want to determine. And you also have an eigenvector X, which of course also carries some information. And this, if you think of the eigenvector, so if you take a quasi-normal mode and you sit on it, then this eigenvector describes, if you extract the expectation values at the boundary, how much each boundary operator contributes to that quasi-normal mode excitation. And that's exactly the amplitudes we are looking for. So it's, we don't really have time that I explain this framework, but if you compute the relative amplitudes in this framework, then you find a numerical value we set it equal to the right-hand side, and we find exactly the same number as we did before in the superfluid phase. So this is also a cool check of this framework of how to compute amplitudes of quasi-normal modes. And again, we determined the constant in both the superfluid phase and the normal phase, and they are both matching, which is another good check of the model. So let's go on and do actual quenches. So we do an exactly critical quench. The analytical solution for exactly critical quenches, you find it by setting rho equals rho 0 in this equation. Then you can solve it analytically just by putting it in dsolve. And what you find is this expression for phi, and you find this expression for the combination of phase and gauge field. And if you plug in our numerical values that we just determined, and you plug in the initial condensate, then you find 4.07, which matches exactly what I showed you in the beginning with the t to 1/2. And you find 0.94, which almost matches the 0.93. The problem here is, and I only noticed it when I prepared this talk, is that we plugged in condensates that were like of order 1 or bigger. We should have done a quench for a smaller condensate, but we'll do that in the future. And then hopefully those two numbers match exactly too, but it's already a very good match. Let's go on and do something which I refer to as subcritical quenches. I don't know if that name makes sense, but I refer to a subcritical quench as a quench where we start in the superfluid phase and we quench near the critical point, but our endpoint, which is the point in green here, is still in the superfluid phase. It's close to the critical point, but still in the superfluid phase. Okay, so the analytical solution in general looks like this. This is the solution for phi, and you find one for the phase and AT, which looks like this. And if you analyze those solutions, then like if you plot them in Mathematica after plugging in all those constants, then you see that you first have a power law decay. So the system first thinks like you're doing a critical quench for some time. And after a time that we call handover towards equilibrium. And this handover time scale can be to first order described as 1 over the deviation of rho from the critical rho. So the closer we get to the critical point, you see this time scale is divergent. So the closer we get, the longer we see this power law decay before we see an exponential decay. And the longer it takes until we get to the critical point. And this is exactly the critical slowing down here. Okay, so we take those analytical solutions. We know all the constants. We can plot it as a function of time. And that's what we do here. So the orange dashed line is our analytical solution to the phenomenological equation for a quench starting with a condensate of 0.1. And we, of course, also know the final rho. So the input here is the initial condensate, and rho is the rho of the final state. Then we can do this time evolution in holography, and this is the blue line that's exactly under the orange curve. So the blue line is our numerical time evolution in holography, and you can see like there's no difference between the two curves. And to guide your eye, I also put the exactly critical quench in this plot, and this is this red dashed line. You see in this regime here, the system falls off with the power law. And this blue dot here is the handover time I talked about on the last slide. And okay, it deviates slightly before that, but it roughly, it gives a good estimate where the system goes over in the exponential decay. And keep in mind, this is a logarithmic plot, so time is logarithmic. This means this is a power law. Okay, this is our first independent check. We can also look at the gauge field. And here, of course, we don't put anything about the quench in our phenomenological equation. So the equation doesn't know what we do. So of course, in the initial time where we change the row, it can't match. But from very early on, it's like t equals 5 or 6, the analytical solution to that phenomenological equation matches the actual time evolution in holography. So we have a very good agreement, not only at late times, but also at intermediate times. Now we can do supercritical quenches, and I refer to a supercritical quench as a quench starting in the superfluid phase that goes across the phase transition to a state that's in the normal phase, but close to the critical point. So we expect an end state without condensate, and okay, we can do the same game. So we have the analytical solution again here. We plug in our initial condensate, we plug in our final charge density. This gives us the orange line. And you see again, for some time, the system decays with the power law before it goes over in the exponential decay. This time the condensate decays to 0. The red dashed line is again our exactly critical quench, and blue is the handover time. And again, even for quenches across the phase transition into the normal phase, the solution to that phenomenological equation matches exactly the real-time evolution. This also holds true for the combination of time derivative of phase and AT. And this plot looks exactly like what we had in the superfluid phase. So I probably don't have to say much about it. Yeah, let me get to the conclusions. So we studied the relaxation of critical and near critical quenches in holographic superfluids. We found a power law decay, and we found phase rotations and a complex critical exponent that hints to discrete scale invariance in the system. We established and successfully tested a phenomenological model that can capture the full nonlinear out of equilibrium dynamics. And all the parameters of that model can be determined either from the static equilibrium solutions or from linear response theory. And I showed you examples. You can determine linear response theory. You can determine it in the superfluid phase, or you can do it in the normal phase, which matches. In the end, we did a non-trivial prediction for the full nonlinear dynamics. And we showed that our analytical solutions of the equation match the actual real-time, the actual nonlinear real-time evolution in holography. And what makes me happy is this is also a nice test and application of our framework to compute the amplitudes of quasi-normal modes that we developed last year in this paper here. And there are, of course, a lot of things to do. So a first step would be to include spatial dependence. I think that's highly non-trivial, but would be very interesting. We could look and perform a similar study, for example, for the case of broken space-time symmetries, if you have spontaneously broken translations, or if you look at other spontaneously broken symmetries in general. And I'd be curious to see if you see something similar. What I would really like to understand is the origin of the discrete scale invariance, of this discrete scale invariance, and if it's possible to maybe relate it to the horizon dynamics. Another thing is, since the system decays in a power law manner, it's basically at equilibrium. So you see how the system balances it and wants to keep the condensate, which decays only very, very slowly. And we already found scaling solutions. So I'd be curious if it's possible to write down a full bulk solution that isn't numerical, but analytically. Then I should probably mention that the amplitude and Higgs mode near the phase transition were recently investigated in the linear regime in holography in this paper, where the authors related everything to horizon quantities and did the bulk expansion. And I'd be interested how those two papers relate to each other and if there are similarities or if there are things different, because we did things that describe similar phenomena from a completely different perspective. Then, of course, it would be interesting to see what happens if we take different types of phase transition. For example, if we have a quantum phase transition, like in wild semimetals, or if we have a first order phase transition. And yeah, let me finish this outlook by saying, of course, it would be interesting to study the physics beyond mean field. Yeah, and thank you for your attention.
Thank you very much, Sebastian, for this very nice talk. And again, thank you for agreeing to present your work on very short notice. I believe we agreed 5 days ago that you would talk about this topic because it was of interest to the organizers. So thank you again for that. So I have two points, but I would like to give the audience a chance to ask questions. Karl.
Hi, I don't know. Can you hear me?
Yeah, we
yes,
can hear you.
We can hear you.
Sorry, I should probably also switch my camera.
We see you.
Yeah,
okay, I don't see myself. So. Yeah, very nice talk, Sebastian. I have a couple of questions. Yeah. And first is you have this phenomenological model, but in the beginning you also presented two other previous phenomenological models. Did I understand this correctly?
Those previous were Ginzburg, dissipative Ginzburg-Landau, dissipative cross Pitaevskii equations.
Yeah. How does your model compare to these models? Can you probably?
Where are they? Yeah, I think it looks very similar to the first equation, I would say. So you replace the chemical potential by the charge density.
Mm-hmm.
And then you have this term that's cubic. We have a few more constants. I don't know, you have to factor this out. So the spatial dependence is not there.
Yeah.
But you have the cubic term and you have the linear term and you have the time derivative on the other side. And you have that complex constant here in front. And if you go to our equation, yeah, again, so we split, this is the cubic term, it's on the left side and on the right side.
Mm-hmm.
So it just has a few more constants in front, but again, we also have the complex prefactor here. Mm-hmm. Then we have this term linear in psi, which has instead of the mu, we have a rho minus rho c. If that makes sense. And yeah, we have the gauge covariant derivative. So this is this is a mu that's multiplying the psi, and we have a rho. So there are differences.
Did you try to match this simpler phenomenological model to your data?
Yeah, I'm sure that's possible.
Okay. Good.
Yeah, you could play the same game. You can where is it? You can look at the model. You can solve it. I think it's very easy to solve it analytically if you don't have that spatial dependence. You just find the psi. If you're then you can do late time expansions, and I think you can try to compare to.
Yeah, if I may quickly interject, I think our model is as simple as we can make it while still fitting everything that we observe.
Yeah.
Especially because, we leave AT to be time dependent. So AT needs to be somehow in the equation. So it has to be more like a Ginzburg-Landau equation than a Gauss-Pitaevskii equation. So in a sense, this gauge invariance has to be included in what we are doing. And that's why we have this gauge covariant time derivative.
Yeah, what we didn't like is, I mean, here you keep a chemical potential constant out of equilibrium. And I don't know, chemical potentials are equilibrium concepts. So shouldn't you work like in an ensemble where you keep the charge density fixed, for example?
Yeah.
And that was our motivation to keep rho fixed instead of mu. So the AT is time dependent, as Mario noted.
Yeah, I see. Very good. Okay. 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 So presumably, I mean, these type of models have been used to match to some experimental data. Could you do this? I mean, could you do this with your model as well? I actually don't know the literature. I have these models here been, applied to an experiment or so. And
yeah, because they study the vortex dynamics and try to compare it to those, or make predictions for vortex experiments.
I see.
Yeah, we want to extend it to
spatial derivative terms, right? Yeah. I see.
Carl, I know you have a few more points, as you said before, but maybe Carlo wants to comment because he also is an author of one of the papers, of the two papers that you're talking about right now.
Yeah. Thanks, Matthias. Hi, Sebastian.
Hi.
So first, let me explain this. Mu is constant because we're using the probe approximation. So if you do a quench or any non-equilibrium, out of equilibrium dynamics, you start with an out of equilibrium situation. Somehow the system will equilibrate eventually, and by that it will kind of lose energy or particles into the black hole if you have back reaction.
Yeah.
Well, in this simple model, we're talking about the parameters actually mu over T. So you would change temperature or vice versa. Chemical potential, but in the probe approximation, there is no change in the horizon, in the background geometry, and that amounts to saying the chemical potential is constant. We just use probe approximation for the quench-like initial condition or for vortex dynamics, whatever, that we put in the initial condition, and then, well, by definition, in the probe approximation, mu is constant. So it makes sense to talk of mu as background chemical potential. I have a question related to that.
Can I also ask? Can I also ask you a question? So the gauge invariant combination is something like time derivative of phase minus the mu. The time derivative of the phase changes. Wouldn't it affect your argument, or how do you keep gauge transformations fixed? Or why does it not affect your observable? Because what I can do is I can change the potential by having a time-dependent phase.
Yeah, probably it will. But let me maybe explain what you said, that we're using, well, the first one in this case of these models as a phenomenological model for holography.
Yeah.
No, we are not. So the purpose of our work is the other group that is cited up there intends to do that. We are not. So what we are trying to do is to determine the parameters of the holographic model, of the vortex dynamics of the holographic model. We do that at large vortex separation with a vortex pair and fit it to a GPE, a particular kind of GPE, but it doesn't matter, because GPEs, any variant of GPEs, actually should work for a dilute system. We know holography is not a dilute system. Actually, we see all kinds of differences once the vortices are closer to each other. They deform in a different way, the annihilation, everything is different. So we are not trying to replace holography by anything else. We're just using this matching to determine the friction parameters of vortices moving in the superfluid in holography. And I don't know why one should replace it. We want to apply holography to, well, if it works, vortex dynamics in a real-world superfluid. Why use a different theory where we know it's different and has different properties and is not applicable to a strongly dissipative case? Why use a different model? The holography calculations are quick. There's no need, we don't need to wait a year for the calculation to be done. We can do it and compare the calculation in holography to data. I don't see the point why this should be replaced, or it's just used, we use it just to determine the parameters of holography, which you cannot extract, well, from just the Einstein-Hilbert action. So that's our purpose. And yeah, but in that sense, I don't care too much which GPE we're using. Okay, we observe that dissipation in holography is different from GPE, and most likely from every GPE. Of course, you could compare different ones and maybe find out a bit more about the holographic dissipation mechanism. That I agree. But in general, we are not trying to replace or describe the holographic superfluid by any such equation, because in principle it cannot work, I think. But let me ask a question concerning this probe approximation. If you do a quench, like you do, you take the system out of equilibrium, it will equilibrate. If you have back reaction included, it will change your mu over t.
Yes. Yeah, that's the point.
Maybe a bit, maybe slightly. Yeah. How would that affect your distinction between a critical quench, slightly critical quench? Because in principle, you don't end up, with back reaction, you wouldn't end up where you end up without.
Yeah, that's exactly the point why we did the probe approximation. Because if you take back reaction, then it's, I don't know, it's extremely hard to fine tune to end up on the critical point. Exactly. As you say, the black hole changes. You don't know where you end up unless you actually do the computation.
Exactly.
And I think it, yeah, especially with those large time scales where you have to do the evolution, I think it would be extremely hard to fine tune to get to the critical point.
Exactly. Exactly.
Yeah.
And may I ask a question? You'd keep rho constant, so that the density is constant?
Yes, we keep rho constant.
Okay. Also, that is probably in the probe approximation. I think that's the main difference between our work and the other work you cite.
Yeah, I know there's some
because we do not impose current conservation, because the system in the probe approximation loses particles to the black hole. And since we have spatial dependence, we also have to do some numerical dealiasing. Also, that loses some particles. So we cannot keep rho fixed. Well, if we do, it would be a driven system. So it's just a different system. And that's
the point why we have to add this null fluid action to our action is because we're in the probe approximation. There's no way to go through the phase diagram if you keep rho fixed. You always end up with the state where you started with. That's why we add this external source in the beginning, so that we can change rho, so that we can actually get to the critical point. You don't have to do this if you have back reaction, because you would move automatically because mu changes. But in the probe approximation, you have to do something that you move. And that's why we add this null fluid action to change the rho initially.
Yeah, I see.
Yeah, this only has to be done because we are in the probe approximation.
Yeah.
Yeah, and thank you for your comment. I didn't mean to misrepresent your work.
It's probably also owed to the short amount of time that you had to prepare the slides. It's hard to do justice to everyone.
Well, yeah, and if you should talk about your own work, you don't talk like 10 minutes about other details.
That's right. Yeah, your paper was very recent. So yeah, thanks, Carlo. Are there more questions? Comments? I had a question regarding if you had thought about the universality classes here. You mentioned that the scalings are all of the mean field type, and so the exponents will be. But there's about 2010, I believe, there was a paper that was stating that like at least in a classical limit, in a large n limit, holography always reproduces the model H, or it falls into the class of dynamical universality classes of Hohenberg and Haltebrunn. That is model H, and that is owed to what you mentioned in the beginning, that the fluctuations are suppressed by 1 over n squared, I believe, in particular interactions between modes. So is there, or between fluctuations, so is there, did you think or check any of this, or is this the part of the conclusions that or outlooks that you pointed out?
Yeah, we should do this more carefully, but yes, the point is here that we have this complex critical exponent, and I'm not sure if they are mentioned in that review where they classify those models. So I'm sure where is it? I'm sure the real part matches because the exponent, but we have the complex exponent here. And yeah, I think it would be very interesting to work this out in the context of this classification and of that review, and make more precise what's actually known and what's new here.
Yeah, so as a comment, the complex part of this complex critical exponent kind of depends on a gauge choice. So what we get in our holographic calculations is that we hold the gauge field to be 0 at the horizon. And then, of course, that implies a split between the gauge contribution and the contribution of the complex phase. If you would change that, then you would get a different complex critical exponent with a different beta, but same alpha.
Yeah, the O here is not gauge invariant. Only the absolute value of O is gauge invariant. Because you can always move phase into gauge field and move gauge field into time derivative of phase. And if you look at the absolute value, then you don't see those log periodic oscillations. They only appear if you actually look at real and imaginary part.
Is this in the broken phase, or?
This is in the this is the content.
Yeah, because I mean, this is something probably for a later discussion, but I'm wondering, Carl had thought about this a lot in the context of the current magnetic effect and the difference, like significance of a chemical potential or the value of a magnetic, the value of a gauge field, if this U1 symmetry is actually broken. So maybe there's something to consider there.
Okay, thank you. I just wanted to comment on that.
Oh, good.
So I think in the broken phase, the gauge field on the horizon actually has to be 0, because otherwise, if you look to the expression for the bulk current, which is basically then, or the bulk charge density, if you so which is basically AT psi bar psi or so. And if this doesn't vanish on the horizon, then the absolute value would blow up. And that is true only in the condensed, in the broken phase. In the symmetric phase, the psi would be 0 and AT can be whatever it wants, at least in a non-equilibrium, so in the Lorentzian section. But I think when you have a condensate, if I'm not mistaken, but I think then AT has to be 0 on the horizon.
Yeah, I try to construct solutions with AT non-zero at the horizon and condensate, but it didn't really seem to work.
Yeah, I think probably something blows up.
It's a regularity condition. AT
has a regularity condition, yeah.
But we are in Eddington-Finkelstein coordinates here, so there shouldn't. Where does the regularity condition come from?
If you translate it from Poincare to Eddington-Finkelstein, you get essentially the same condition. Well, it's mapped to a time coordinate very large t, but AT still vanishes, I think.
Hold on, can you say that again? What happens at large T?
If you change from Poincare, where you have this condition, it's a regularity condition, AT multiplies, as was said before, something, so that has to be 0. If you transform the whole thing to Eddington-Finkelstein coordinates, if I remember correctly, AT is still 0, but of course you change coordinates, time and so on. You map it to infinite time coordinate, I think, in Poincare.
Yeah, but
that is still 0 because it's 0 all the time. So AT has to vanish in Eddington-Finkelstein as well.
But we want to keep radial gauge, so the AT is. You need in Eddington-Finkelstein, for example, you need a complex scalar to impose radial gauge if you would move to Poincare coordinates. So I'm not sure if I understand the argument.
Okay, I think we have to check, but
yeah, maybe something for an email exchange or yeah, that's at least good to see that there was some discussion spawned there.
Yeah.
I had just one more comment on our suggestion, and that was maybe use a P-wave superconductor for the analytic solution that you desired, because you pointed out that you wanted to one question mark was maybe find analytic solutions on the holographic side. And then there was this Basu et al. Paper that found at a particular value of the chemical potential mu equal 4, they find the analytic solution in a P-wave setting. More complicated setting, but it also realizes another point on your wish list in the Outlook, which is the break spatial symmetries.
Yeah.
If you have not already thought of that, then that was my comment. But yeah, that would be exciting. So any more questions? If not, then we can move on to an informal minute. But before that, I'll thank Sebastian again and thank everyone for the lively discussion.